Welcome to today's lecture. In the last class of Geotechnical Engineering, we have discussed about how to perform CO analysis on fine-grained soils as well as coarse-grained soils. And we have also discussed about what are the different volumetric relationships, mass-volume relationships, volume-weight relationships, and weight relationships. Right? Now in today's class, we are going to talk about the index properties of soil or the consistency limits of soil. Okay, so to begin with our lecture, we are going to talk about the index properties or engineering properties or generally the properties of soil. Okay, so initially before we talk about the index properties of soil, it is very important to know what are the different types of soil exhibits or what are the different properties that a soil exhibits. So broadly, any type of soil exhibits two different properties. Those two properties are, one is engineering properties and the second one is index properties. Okay, so these are the two properties which are exhibited by any type of soil. So the soil properties are broadly classified into index properties and engineering properties. So under engineering properties, we can say the different engineering properties such as permeability, compressibility and shear strength. Okay, so there are three engineering properties available for any type of soil. The first one is permeability, second one is compressibility, and the last one is shear strength. Okay, so we'll talk about permeability, compressibility and shear strength in the next unit, but this unit or this discussion is limited to a discussion on index properties of soil. Okay, now these index properties of soil are again broadly can be classified into two types. One is index properties related to coarse grained soil and index properties related to fine grained soils. Okay, now what do you mean by index properties of soil? Okay, so we'll talk about the engineering properties in the later classes, but we focus now on index properties of soil. Now if you take any soil sample from a given particular area or particular location, any soil does possess different properties of a particular soil sample. Okay, it is not sure that all the properties will exhibit same properties of soil. It is different. So each type of soil, based on the location, based on the climatic condition, based on the weathering actions, so based on various properties, the soil parameters will get changed. Okay, now what does this index properties says is the properties which facilitates the identification and classification. Okay, these index properties are basically helpful for the identification and classification of soils. Okay. Now we have seen when we are discussing in the first lecture, we have talked about different types of soils such as aeolian soil, alluvial soil, lacustrine soil, marine soil, glacial soil and colluvial soils, right? Now, how did you classify these soils? How did you name a particular soil as an alluvial soil? Or how did you name a particular soil as a glacial soil? It all depends on the properties which are exhibiting by that particular soil. So, in order to identify or in order to classify the soils based on the properties, so when you are classifying any soil based on the identification and classification, such kind of properties are called as index properties. So usually index properties can be defined as the properties which are helpful to identify a particular soil and to classify them into a separate group. Okay, so it is very important to identify a soil and to classify the soil. It is not just identification of soil that is more important. So once you identify the soil, it is very important to place a soil which belongs to that particular group. So we'll talk about different groups of soils in the later stages, but for now, if you remember the periodic table which is available in chemistry, so you will see different elements or different atoms or the atomic arrangement of the various elements, right? So helium, neon, argon, krypton, xenon and hydrogen, helium, like we have different elements are available. So all the elements which are available in the periodic table, they are arranged based on their atomic weights or based on their properties which are getting exhibited, right? So if you take helium, neon, argon, krypton and xenon, you say that these are the elements which possess inert properties, or these are the gases which are called as inert gases. So how did you identify these inert gases, or how did you classify these particular elements as inert gases or inert elements? Because of its properties. So similarly in soil also, it is basically important to identify the soil, and it is also much more important to classify the soil or to place the soil under a particular group or under a particular tree. Okay. Now these index properties for coarse grained and fine grained soils are again, the coarse grained index properties are of two types and the fine grained index properties are of two types. So we'll talk about that. So when it comes to the coarse grained index properties of soil, so in order to identify the coarse grained index properties of soil, we have two things. One is particle size and the second one is relative density. So we have already seen about the sieve analysis of soil, that is particle size distribution curves as well as particle size or the gradation curves. Right? So that is all about the gradation or the particle size distribution when it comes to the coarse grained index properties. So the other property which we have seen in the coarse grained index properties is the relative density. Right? So we have seen, or we have identified the two different methods to identify the or to find out the density or unit weight of a soil, basically dry density or unit weight of a soil. So if you remember the last class, we have talked about the dry density of a soil sample in the field can be determined by using two methods. The first method is sand replacement method and the second method is core cutter method. Right? So these are the two things which are available under coarse grained index properties. But when it comes to the fine grained index properties, we have two types. One is the Atterberg limits. Atterberg is the name of a scientist where he classified the soil into different states. So we'll talk about that in a later stage. So this is the first property, which is Atterberg limits. And the second one is consistency limits. Okay. So now our lecture or this lecture will focus on the discussion of the Atterberg limits and consistency limits. They both are same, but however it depends on various properties. So we'll talk about Atterberg limits and consistency limits now. Right? Now, before we talk about the index properties or the consistency limits or the Atterberg limits, I want you to understand what do you mean by plasticity of a soil. So you all know plasticity of a soil can be defined as the ability of a soil to undergo deformation without any cracks or without any fracturing process. So in order to define plasticity or a plasticity of a soil can be defined as such property which can undergo into deformation. You have clay, for example you take clay. So clay can be molded into any shape without getting fractured. So when you are able to mold any clay or any soil material without making the fracture surface or without creating any fractures, so such kind of property is called as plasticity of soil. I hope it is clear for everyone. So the plasticity of a soil can be defined as ability of a soil to undergo deformation without any fracturing process or without any cracks. This is how in simple terms you can define plasticity. So the best example for plastic material is clay. So clay can be molded into any shape of your convenience. If you see Ganesh idols or any other idols, so all these idols are usually made by using clay, and nowadays clay has stopped being used and we have modified the Ganesh idols by using plaster of Paris. However, it is harmful. Okay. Now coming back, so here the clay can be molded into any shape. That means all the plasticity properties which are exhibiting by different soils, they can be molded into any shape. So remember, whatever the soil it is, if a soil or if a sample of any soil sample is exhibiting plasticity properties, it means it can be molded into any shape of our convenience. The next important thing is, why does plasticity happen? It is basically due to presence of clay minerals. So inside clay there are some minerals which helps the clay particle can be molded into any shape. Suppose if you take a sand sample or a sample of sand, so you cannot mold a sample of sand into any shape of your requirement because you don't find the soil sample to flexibly move, right? So In order to understand the plasticity of soil, it is very important to identify or to understand how actually the clay behaves, or how can we convert clay into any shape of our convenience. It is very important to identify that. So if you are able to convert, or if you are able to modify clay into any shape of any required property or required convenience, it is all because of the minerals which are available in clay. So these minerals which helps clay are broadly classified into 4 types. So the clay minerals can be broadly classified into 4 types. Those are, the first one is kyanite, illite, montmorillonite. So broadly there are 3 types. So there is also one more type, which is the other one, which is mesoite. So we'll talk about the clay minerals in the later stages. But remember, the clay can be molded into any shape. It is all because of the presence of clay minerals such as kyanite, illite and montmorillonite. Okay. So now the next thing is, we'll talk about the consistency of soil, or the consistency limits of soil. So you all know that. Now take a live example. Suppose when you are watching cricket commentary, the speaker says, or the commentator says that he or she has been performing a consistency throughout this series. What does this indicate? Consistency means without any drop of the various parameters. Suppose if he is from batting department, he is consistently batting at a very good rate. That means he might be performing at a very good rate. So similarly, soils will also have the consistency limits, or the consistency indices. So broadly, these classic consistency limits depends on the water content. Okay? So water plays a major role in defining the consistency of any soil. So if you use high amounts of water content, the consistency of soil varies, and if you use low amount of water content, the consistency of soil again changes. So if you want to identify the consistency of any soil sample or any clay sample, it is all because of the presence of moisture content. So it is very important to identify how much amount of water is required to make any soil sample into a consistency state, or into a proper state which is helpful for the construction activities. So now the next thing is, it is also called, the consistency limits is also called as Atterberg limits. So Atterberg is the name of a scientist who coined these consistency limits, and upon his name these consistency limits are also called as Atterberg limits. The next important thing is, depending on the moisture content, the behavior of the soil can be changed. It is all, you know this, right? So when you use high amounts of water, the soil will be converted into a liquid material. When you use sufficient amount of water content or the moisture content, the consistency of soil will be very solid or semi-solid in state, right? So based on the amount of water content that is being added in the soil sample, the consistency can be divided into 4 types. One is the solid state, second one is the semi-solid state, third one is the plastic state, and the last one is liquid state. So these are the 4 states which are available in a soil sample based on the water content. Suppose if you take the last one, which is liquid state or the liquid limit. So what does this liquid limit indicates? If you are using high amounts of water, suppose say for example you have taken 100 grams of soil sample and you are using 3 liters of water. So when you use 3 liters of water with 100 grams of soil sample, obviously the soil sample will be very liquidous, right? You don't find the soil sample to be mixed properly because high amounts of water is available, and hence the soil becomes liquid substance, or the soil behaves like a liquid material. Okay? So when you use sufficient amount of moisture content or sufficient amount of water for preparation of soil, the soil sample can be converted into solid state or semi-solid state. It depends again. So it all depends on, these 4 stages are depending on the water content. So to simplify this slide, we can say that the water content plays a major role in defining the plasticity characteristics of a soil sample as well as consistency limits of a given soil sample. We will talk about each one of the 4 phases, that is solid, semi-solid, liquid and plastic stages. Okay. Now, to begin with, we know that consistency limits are also called as Atterberg limits. So there is also another name which is for consistency limits is consistency indices. Okay. So before we talk about the different types of consistency limits, I want you to understand what actually I mean by consistency limit. That means that is the limit of the water content which stops or which gets exchanged into the next phase. Okay. We have seen 4 phases, right? Solid, semi-solid, plastic, liquid. So these 4 stages will vary based on the amount of water that is being used. So we'll talk about the consistency limits or the Atterberg limits. We have 3 different types of consistency limits. The first one is liquid limit. So liquid limit can be simply written as LL, capital L, capital L, or it can also be written as small w suffix L or WL, where W represents the water content which is available in a soil sample, right? So in this state, as the name itself says, in liquid limit, what actually happens is, it is the minimum water content at which soil changes or the soil will flow under its own weight. So as I said earlier, you took 100 grams of cement and you take 3 ml or 3 liters of water. When you mix 100 grams of soil sample with 3 liters of water, obviously the soil will convert into a liquid state, or the soil will behave as a liquid, right? So such limit is called as liquid limit. So here in liquid limit, the soil will flow under its own weight. You don't need to give any extra pressure or any extra push to move the soil sample which is in liquid state. It flows on its own weight because high amounts of water content is available in the liquid limit. Now in liquid limit state, the soil will convert into liquid state to plastic state. Remember, in liquid state, the soil converts into liquid state to plastic state. So you all know plasticity or the plastic limit defines as without making a fracture or without making a cracks, you can remold the clay or you can mold the soil sample into our convenient shape. That is what plasticity defines as. So liquid limit is the minimum water content at which soil flows under its own weight. And in liquid limit state, the soil converts from liquid state to plastic state. The soil stops behaving like a liquid member and hence it converts into the stage of plastic state. Okay. So the next one which we are going to talk about is plastic limit. So the plastic limit is defined with a symbol PL or WP. So W suffix P indicates plastic limit. So where again small w represents the water content which is available in a soil. So how will you define this plastic limit? So the plastic limit is the minimum water content at which change in shape of a soil is accompanied by visual cracks. So what does it mean? So in plastic limit, the change in state can be observed by observing cracks on the surface of the soil sample. So we have a test which is to identify the liquid limit of soil as well as the plastic limit of soil. But remember, in plastic limit, you can see the change or you can see the modification tendency of soil by observing the cracks on the surface of a soil sample. This is how it is available. See here you can see the cracks are available on the surface, on the top layers, or which got extended throughout the member or throughout the soil sample. So these are the cracks. When you identify these cracks, you can say that the soil is converting or the soil is in plastic state, right? So this shows that the amount of water content which is used to prepare or to convert a soil sample into plastic stage is not sufficient enough, right? When the amount of water content which is required is less than what is to be used or what has to be used, it shows the cracks on the surface of the materials or surface of the soil sample. So in plastic limit, the soil converts from plastic state to semi-solid state. So from here, that means once after the plastic state is reached, the soil starts converting into a semi-solid state or a hardened member. Not pure hardened, it doesn't get complete hardness to the soil sample, but it does starts changing into a semi-solid state. This is what the plastic limit is. Whereas the next one, which is the last one, is shrinkage limit of soil, which can be defined by using symbol SLRWS. Again, the W represents water content. What does the shrinkage content indicate, or the shrinkage limit indicates? So it is the maximum water content. Remember, it is the maximum water content at which further reduction in water content will not cause a decrease in volume of soil mass. Again, go back to the definition. So shrinkage limit can be defined as the maximum water content at which the further reduction in water content will not cause decrease in volume. That means up to some extent the soil volume changes, but if you further reduce the amount of water content, the volume of the soil doesn't change. So this state is called as shrinkage limit, and this is the stage where shrinkage will stop. Okay, shrinkage limit, what does it indicate? The shrinkage is getting limited, or the shrinkage is getting stopped at this stage. You don't find any amount of volume change if you go on decreasing the water content. That is what the definition says. So the definition, once again we talk about that, that is, it is the maximum water content at which the further reduction in water content will not cause a volume change, and this property is called, or this limit is called as shrinkage limit. In shrinkage limit, the soil converts from semi-solid state to solid state. This is the hardened mass of a soil sample. So whatever the soil sample that you are seeing in real-time scenario, all those had reached their shrinkage limit, or probably most of the soils had reached their shrinkage limit. So we have different experiments to identify the liquid limit, plastic limit and shrinkage limit of soils. We'll talk about the experimental procedures in the next slides. Okay. So here, in order to identify the shrinkage limit of soil, you can clearly identify the color of the soil will change from dark color to light color. Okay. So when will you say any soil sample has reached shrinkage limit is the soil sample, or the color of the soil sample will change from dark color to light color. So these are the different consistency limits or Atterberg limits which we have. Now the next thing is, observe this graph which is provided here. On the x-axis you are provided with the water content, and on the y-axis it is the volume change. Okay, so x-axis represents the amount of water content, and y-axis represents the volume change of a soil sample. Now if you observe from the top end to the bottom end, that is from the top axis which is at the liquid limit to the bottom axis which is at the solid state. So here the curve is getting flattened, right? So the curve is decreasing in this way, right? So initially what does this curve indicate is, as the amount of water content decreases, right? It comes from the top to the bottom end. So as the amount of water content decreases from top end to the bottom end, the soil is getting converted from liquid to plastic state, plastic to semi-solid state, and semi-solid to solid state. Okay, I hope it is clear for everyone regarding this. So what actually happening here is, so the soil, with the decrease in the water content, the soil property is getting changed from liquid state to solid state, right? Now if you observe the clear difference between the solid, semi-solid state and solid state, it is represented by a straight line, right? Observe the phenomena very clearly here. In the liquid limit, it is a curve starting from the liquid limit to till the end of semi-solid state. It is a flattened straight line. Okay? It is an inclined straight line. That means what does it indicate is, with the decrease in the water content, the shape of the soil sample, or the limit of the soil sample, is getting changed from liquid state to plastic state to semi-solid state. Now when you observe the difference between semi-solid state and plastic state, this is the state where shrinkage limit happens. If you further reduce the water content, there won't be any change in the volume of the soil. That is what the definition of shrinkage limit said, right? So if you want to further decrease the water content, there won't be any change in the volume of the soil, or there won't be any shrinkage in the soil. That is why it is a rectangular box. It is not a sloping curve, or it is not a declining straight line. So here in the solid state, the soil behaves as a flat curve or the flat line. It is because of it reached its shrinkage limit. Even if you add or even if you remove the water content from this solid state soil sample, there won't be any change in the volume, and this state is called as shrinkage limit, or this limit is called as shrinkage limit. I guess now you have got an idea of how the water content plays a major role in defining the various states or the liquid or the various consistency limits or the Atterberg limits of a soil. Okay, fine. Now moving on, we'll talk about plasticity index of soil. So the plasticity index can be defined as Pi or I suffix P. So remember, plasticity, we know about plasticity. Now what does this plasticity index is? It is the water content at which soil exhibits plastic properties. So remember, it is the water content. Plasticity index is the water content at which soil exhibits plasticity characteristics or the plasticity properties. What are these plasticity properties, or what are these plasticity characteristics? So going back to the definition of the plasticity can be defined as when you add sufficient water content, you can mold the clay or you can mold the soil sample into any shape without getting fractured. That is what the plasticity characteristic is. Okay, so the plasticity index can be defined as the water content at which the soil exhibits plastic properties. That means you don't find any cracks on the surface. Instead, you can mold the soil sample into any shape of your convenience. Now the next thing is, plasticity index is the difference between liquid limit and plastic limit, LL minus PL. So LL represents liquid limit and PL represents plastic limit. Okay, now so these are the various plasticity indices of different soils. When the plasticity index is 0, the plasticity of such soil is said to be a non-plastic soil. That means this soil doesn't possess any plasticity characteristics. So when the plasticity index is in between 1 to 5, it is said as slightly plastic soil. That means this soil will exhibit slight amount of plastic characteristics. Likewise, you have 5 to 10, 10 to 20, 20 to 40 and greater than 40. So when the plasticity index is greater than 40, you can say that this soil is very highly plasticity properties, or this exhibits, or that soil exhibits high amounts of plasticity characteristics. So this is all about the plasticity index of soil. Okay, I hope it is clear. So once again, so it is all said that the water content at which soil exhibits plastic characteristics is called as plasticity index of soil. So the plasticity index is the difference between liquid limit and plastic limit. Right? Now coming back, we have different classifications of plastic properties of soil, and these classifications are made by a scientist called Burmister. So and hence upon his name we are going to call these characteristics as Burmister classification of plastic properties of soil. So we'll talk about what are those classifications and how actually Burmister classified the various plastic properties of soil. So the first one is shrinkage index. We have talked about shrinkage limit, right? Now we'll talk about shrinkage index, that is defined as SI, or capital S, capital I, or it can also be defined as I suffix S. Capital I represents index and S represents shrinkage or shrinkage index. So it is the ratio, or it is the difference between two parameters. The difference is, it is the difference between the plastic limit and the solid limit. Right? So understand clearly, it is the difference between, the shrinkage index is the difference between PL and SL. So PL represents plastic limit and SL represents shrinkage limit. So remember, so shrinkage index is the difference between the plastic limit and the shrinkage limit. So usually the shrinkage index of a soil can be identified when the soil is in semi-solid state. Right? So in shrinkage limit or in shrinkage index, the soil is in semi-solid state. So the next property is consistency index or CI or IC. I represents index and C represents consistency. So in this, the soil behaves like a consistent material, or usually the soil will be a consistent material. It is also called as relative consistency. Okay? The consistency index is also called as relative consistency. It is the difference between the liquid limit minus water content upon plasticity index. So the consistency index is CI equals to liquid limit minus water content upon plasticity index. PI represents plasticity index. So we have different ranges to identify the consistency index of a soil. Those are all these. So when IC, that is when consistency index is 0, water content of such soil is said to be in liquid limit state. When the consistency index is 1, water content of such soil is in plastic limit. Whereas IC is greater than 1, soil is in semi-solid state and the soil behaves like a stiff member. When the IC value is less than 0, soil is said to be in liquid state. Okay? So this is how you can classify the consistency indices based on different ranges. Now the next important thing is liquidity index or LI or IL. So this liquidity index is also called as water plasticity ratio. So liquidity index can also be called as water plasticity ratio. It is the ratio or it is the difference between water content minus plastic limit upon plasticity index. Okay? The liquid index or liquidity index can be defined as the difference between the water content and plastic limit upon plasticity index or plasticity index. Okay? So this liquidity index is again classified into various types. Those are when the liquidity index is 0, the water content is said to be in plastic limit state. So when the liquidity index is equals to 1, the water content is in liquid limit state. Now you observe the consistency index limits and the liquidity index limits. So when IC is equals to 0 in consistency index, W equals to LL. Whereas in liquidity index, the property is suddenly getting changed. That means the soil is converting from liquid state to plastic state in the second phase, that in the third phase, which is in liquidity index. So similarly, when IL equals to 1, the soil or the water content behaves like a liquid limit state. Whereas in the previous one, that is in the consistency index, when IL equals to 1, water content equals to plastic limit, or the water is in the plastic limit state. So similarly, when IL is greater than 1, soil is in liquid state, and when IL is less than 0, soil is said to be in semi-solid or stiff state. So this is the clear-cut difference between the consistency index and the liquidity index. Now, going back, the consistency index can also be defined as the difference between, the consistency index plus liquidity index is always equals to 1. Okay, so remember, the consistency index and the liquidity index is always equals to 1. Okay, so these are the different Burmister classification of plastic properties of soil. So these are all the plastic properties of soil. One is shrinkage index, the second one is consistency index, and the last one is liquidity index. Okay, I hope it is clear for everyone. Now observe this figure, the same chart once again I am showing here. So here again, once again you observe on the x-axis it is water content, and on the y-axis it is the volume change or the change in volume of a given soil sample. So when the water content is decreasing from the top end to the bottom end up to semi-solid state, it is, the line is declined, or you can see a declined line. But when it comes from semi-solid state to solid state, it's a flat line. What does this represent? This is the state where shrinkage index happens. This we have talked about it earlier. Now you observe the different indices here. So liquid, plastic, semi-solid and solid. So in plastic, again you have three different types. One is low plasticity, medium plasticity and high plasticity. This we'll talk about when we are talking on the different classifications of soil. So remember, under plastic limit or under plastic state, we have three different types. One is high plasticity, medium plasticity and low plasticity. These are the three different plastic ranges when the soil is said to be in plastic state or the plastic limit. Okay, so how will you determine the liquid limit of a soil? So this is most important. So in order to determine the liquid limit of a soil, we have to understand an apparatus called Casagrande apparatus, whose name is Casagrande. Okay, so upon his name, he made an experimental procedure which says that Casagrande method to identify the liquid limit of soil. Okay, so Casagrande is the name of a scientist, and we also have one more method to identify liquid limit of a soil, which is cone penetration method. So we have two methods, one is Casagrande method and the second one is cone penetration method. But however, we don't generally use cone penetration method, but most of the times we prefer using Casagrande method in order to identify the liquid limit of a soil or the liquid state of a soil. Okay. Now I observed this video and clear cut definition of liquid limit and how to identify or how to determine the liquid limit of a soil sample can be shown here. So please watch the video.
We can determine the liquid limit by two laboratory methods, Casagrande method and cone penetration method. In this video, we will discuss Casagrande's method. For the determination of liquid limit by this method, we make use of an apparatus which is called the Casagrande apparatus. It consists of a brass cup which is connected so that it is in the inclined position when resting on the rubber base. Brass cup, when rotated by its handle, lifts to the height of 1 cm and drops freely on the rubber base. To begin with, we take the soil sample and air dry it. Then we pass it through the 425 micron IS sieve to get the fine grained soils only. Because we know Atterberg limits are only significant for the fine grained soils. 425 micron IS sieve has its mesh openings of 425 micron or 0.425 mm. The particles we get after the sieving are all of the size less than 0.425 mm. These particles include fine sand, silts and clays. Then we take about 120 gram of this sieved soil in a dish and mix it with distilled water to form a uniform soil paste. A portion of this soil paste is placed in the cup of Casagrande's apparatus and the surface is smoothened and leveled. Then a sharp groove is cut symmetrically through the sample using the standard grooving tool. No, we do not use our finger as a standard tool. But there are two types of standard grooving tools available. One is Casagrande tool and other is ASTM tool. This is Casagrande tool. And this is how the soil profile will look like when the groove is cut. This tool cuts the groove of width 2 mm at the bottom and 11 mm at the top and 8 mm deep. And ASTM tool cuts the groove of width 2 mm at the bottom, 13.6 mm at the top and 10 mm deep. The Casagrande tool is recommended for normal fine-grained soils. After the soil pad has been cut, the handle of the apparatus is turned at the rate of 2 revolutions per second, which applies blows to the grooved soil pad, and due to which 2 halves of the soil pad come into the contact. And when the contact length of 12 mm is achieved, we stop turning the handle. We should take care that the groove should close by the flow of soil, not by slippage of it. And if slippage occurs, then we should discard that soil pad and redo the whole procedure. The contact distance of two soil halves is measured with a ruler. The number of blows required to close the groove for the length of 12 mm is noted as N1. About 10 gram of soil near the closed groove is taken for the water content determination. Water content is determined using any of the water content determination methods. Determined water content is noted as W1. The liquid limit has been defined as the water content of the soil at which the groove closes to 12 mm in 25 number of blows. That means our observation of water content W1 could be the liquid limit of our soil sample if the number of blows given to the soil sample N1 was 25. But practically it is difficult to get exactly 25 number of blows for the 12 mm groove closure. So we conduct the test for different water contents so as to get the number of blows in the range of 10 to 40. Hence, the experiment is repeated 3 more times after adding more water to the soil, and each time recording the number of blows to close the groove for a distance of 12 mm and determining the corresponding water content. Soil with low water content would yield more number of blows as the soil paste will be stiffer, and soil with higher water content would yield less number of blows. We plot a graph between these experimentally obtained values of number of blows and their corresponding water content. The number of blows are plotted on a log scale. A best fitting curve is drawn through the experimental points, and we will observe the graph will be approximately a straight line. This curve is known as flow curve of soil. The water content corresponding to the 25 number of blows is read from the graph and is taken as the liquid limit. The liquid limit is expressed as the nearest whole number. Now let's look at the flow curve of two different soils. If we draw a line from 25 number of blows, we can see soil 1 would reach at liquid-like state at water content LL1, and soil 2 would attain the same state at water content LL2. Clearly, LL1 is higher than LL2. Soil 2 has liquid limit value less than that of soil 1. Soil 2 will become and behave like a liquid at lower water content compared to soil 1. In other words, we can also say that if we keep on adding water to both the soils, the soil 2 loses its shear strength and becomes liquid-like earlier at lower water content than soil 1. Liquid limit of soil can also be determined by another method called cone penetration method.
Watch the video and I guess you have understood how to determine the liquid limit of a soil sample. Now we'll see an experiment which is used to identify the plastic limit of a soil. Okay, so we already discussed that plastic limit is the limit where you will observe the cracks on the surface of a material or surface of a soil sample. Till the time the cracks are able to identify, such state is called as plastic state. So please watch the video and understand how will you determine the plastic limit of a soil in the laboratory purposes.
Plastic state, soil can be rolled into threads without breaking them, and it can be molded in any shape. Plasticity of soil is calculated in terms of its water content. As the water content of the soil is reduced, the plasticity of the soil is also reduced. While soil is in the plastic state, if we reduce its water content, soil reaches a point below which it stops behaving as a plastic material. That water content is called plastic limit of soil. At this water content, soil loses its plasticity. Below the plastic limit, soil begins to crumble when rolled into threads of 3 mm diameter. We can determine the plastic limit using the soil sample prepared for the liquid limit test. For the determination of plastic limit, the soil is air dried and sieved through 425 micron IS sieve to get fine grained soils only, because we know Atterberg limits are only significant for the fine grained soils. 425 micron IS sieve has its mesh openings of 425 micron or 0.425 mm. The particles we get after the sieving are all of the size less than 425 micron. These particles include fine sand, silts and clays. We take about 30 grams of this sieved soil in an evaporating dish. It is thoroughly mixed with distilled water till it is reached at a consistency at which it can be rolled without sticking to the hands. We take some amount of this soil mass in hand and form a ball. Then the ball is placed on the glass plate and rolled between the palm and the glass plate with little pressure to roll the soil mass into thread of uniform diameter throughout its length. The thread shall be further deformed on each stroke so that its diameter reaches 3 mm, taking no more than 2 minutes. We take the reference of a metallic rod for the diameter comparison of the thread. Normally 80 to 90 strokes per minute are recommended. We count a stroke as one complete motion of the hand forward and back to the starting position. If the diameter of the thread becomes smaller than 3 mm without any crack formation, it shows that the soil is in plastic state and its water content is higher than the plastic limit. The plastic limit is the water content of the soil at which soil just begins to crumble when rolled into threads of 3.2 mm or 1/8 of an inch in diameter. If rolled threads does not crumble while reaching at 3 mm diameter, then it is kneaded into a ball again and its water content is reduced by continuously spreading and mixing the soil on the glass plate. After that, the soil is re-rolled into a thread and the procedure of kneading and rolling is repeated until the thread begins to crumble. Once the thread crumbles, it means that soil has reached its plastic limit. We collect the soil pieces and its water content is determined using any of the water content determination methods. Its water content is noted as W1. We repeat the whole procedure 2 more times, taking the fresh soil sample each time. We determine the water content W2 and W3 respectively. Average of these 3 determined plastic limit water contents is considered as the plastic limit of that soil. When the water content of the soil falls below the plastic limit, soil enters into the semi-solid state.
Now I guess everyone had understood how to determine the liquid limit and the plastic limit of a given soil sample in the laboratory. So in the next class we'll talk about the activity of clay or the activity property of clay. Okay. See you in the next class. Thank you.